All right. Hi, everybody. I'm Chris Brousseau, and this is Abstracting Hype, where I'm going to be peeling back some layers of NLP to help you figure out how to get the most out of not just your large language models, but your language models in general. And everything I'm going to be saying will be applicable, obviously, to large language models, so feel free to use it in that capacity. So here is a little bit about me. I did my undergrad in linguistics at BYU. I really love languages, and I love looking at the intersection of natural human languages with computers. I've been married for 6 years. This original presentation was given in March, but we're in April, so 6 years this month. And I have two little blonde boys, Odin and Magnus. They are really silly little guys, and I love using NLP to help them interact with the world on a higher level. And I currently work as a lead data scientist on MasterCard's international open banking team. I love doing that. So here, let's start with a really broad question. What is language? And we're looking for probably 5 features that we can see. There's some debate about how many there actually are, but there are 5 generally agreed upon features. Those are semantics, those are pragmatics, syntax, morphology, and phonetics. And we'll go into a bit about what all of these are. For now, let's focus though on language as a concept. Actually, I'm going to go back and let's talk about semantics is generally your encoded meaning. So when you talk about what a word literally means, that's your semantics. Your pragmatics is your contextual meaning. So when you're talking about meaning that you can only get from like being with someone or knowing about how something works or having lived in a culture kind of thing, that's pragmatics. Syntax is your actual grammar and structure to language. So it's going to be your clauses, your structure around around sentences, around phrases. Morphology is your structure around words. The idea that re has meaning by itself in relearn or redo, but like ration, like ra doesn't necessarily mean anything as in ration, or na doesn't necessarily mean anything like in nation, even though shun probably does mean something. That's your morphology, is the structure of words. And then phonetics is going to be your actual speech, like the sounds that come out of your mouth. All right, let's hit this now. Language as a concept is already an abstraction of feelings informed by experiences, encodings, and rituals, right? So you have feelings and thoughts that are just in your brain, and you end up using language as an abstract medium to communicate those to somebody else. Meaning within that language is inserted sequentially by the listener as that process of interpreting language occurs. I mean, you can have meaning that you intended, but it doesn't always get across that way, and that's why I've drawn this boundary, that meaning is inserted by the listener. And when we think about this in the context of models, meaning is inserted by the model, right? So let's hone in on the parts of language that we had related with meaning here. We have syntax, that structure, semantics, the encoded meaning, and pragmatics. I want to give us some examples to help us figure out better what this actually means. How does it apply? So syntax, a lot of people will argue that syntax is separate from meaning, and I think that largely that's true. In 99.9% of all cases, that's true. But it's just the structure, it's your grammar. If you took English in high school, you likely talked mostly about syntax. If you took English or editing in college, you probably mostly talked about syntax. And you would have gotten into other things too, obviously, but your main study would be that syntax. And that we'll get into why that is in a minute. This is also what models mainly use. So we'll talk about now semantics. The difference between semantics and pragmatics, if you're not sure yet. Semantics is when you say something that has conflicting meaning. So for example, if I were to say that I'm married to my ex-wife, you can immediately have questions because there are pragmatic explanations for that. Maybe I'm remarried or something along those lines. But ex-wife generally means, well, not just generally, it's encoded as to mean we're no longer married. And so that refutes the meaning of currently married. So that's a semantic problem. Whereas pragmatics would be if somebody told me your best friend was rushed to the hospital, I can assume that they are hurt. And that had nothing to do with the literal meaning of anything that they said. What it does have to do with is me living in a culture that has hospitals and knows what that means. Being rushed to the hospital as opposed to walking into the hospital have different meanings, right? And those meanings are not encoded directly in the words, they're kind of in the spaces between the words. So this is meaning in language. This is generally the sequence that we follow when we are trying to interpret language. And this is a pretty minimalist version of what we're going for here. I mean, it's, if you're familiar with semiotics, if you've seen any Persian triangles before, this should look familiar to you. If you haven't, don't panic. This is just to kind of help us connect everything together. I think the best way to illustrate this is to just imagine taking some of these things out. So if you start in the top left with that qualisign feelings and go down diagonally, down to image senses, static signals, action triggers, that's your first pass in this organization table. And we call that the experience path. And if you can imagine, if we take any of these out, that's how we know that they're actually essential. If we take out images from trying to interpret this presentation that you're watching, and it's just a blank screen, it becomes difficult to interpret, right? If we take out static signals, so some static signals here are like the white space between the triangles, the fact that it's an actual shape, any bullet points that you see. Those are static signals around the text telling you where to look next and giving you a flow for it. If we take those out, it becomes difficult to interpret. I'm not going to go over all of these, but what I want you to be thinking about as you watch the rest of this is, what are the parts of this organizational structure for interpretation and creation of meaning? What are the parts of this structure that LLMs actually have access to as they are trying to interpret language? Right? What does a computer use currently? And we've already talked about it a little bit. The computers generally, we've struggled mathematically to represent language in a really good way to computers over the course of our time with them. And so let's take a look at a couple of language models that we can create. Let's say we're using a Bayesian statistical model, a naive Bayesian statistical model to model language, right? How do we do that? With naive Bayes, we generally get a log prior and we get a log likelihood for every word contained in our whole vocabulary. What that does for us is it allows us to confirm hypotheses based on those log priors and log likelihoods. You may already know this weakness, though. If you look here at this sentence, I love this fun film, right? I has a static value for positivity and negativity. Can you think of some sentences where I could be both positive and negative? Or can you think of some sentences where I sounds positive, but it's not? Like, I'll give you an example. I love that for you, right? That sounds generally like a positive sentence, but because of the pragmatic context that naive Bayes models are missing, it doesn't. It doesn't always mean that. It can mean that, but you're going to need more information. You can't just analyze that only from the text. Or if we take a look at any demonstrative pronouns like this, right? This has a static, at least in most naive Bayesian models, this or that or it end up having static values. But the fact that they're adding any value as opposed to adding a zero just belies that naive Bayes doesn't know what to do with words that have multiple meanings. And this is in the context, obviously, of semantic analysis, of sentiment analysis. So that's why we're talking about it in terms of positivity and negativity. It's difficult to use naive Bayes as like a generative language model. It's more evaluative. But within that context, we can see that there are some inherent problems due to naive Bayes not capturing all of the information that we want it to. The last thing that we struggle to capture with naive Bayes is an actual long-term dependency, or looking at a whole sequence as a sequence in order, as opposed to looking at each individual word by itself. And that ends up just being a summation every time, and that doesn't capture those long-term dependencies. That doesn't capture reference way back in a paragraph the way that we do when we're speaking to each other. And if we go down to the second half of this, we have n-grams, right? So this is a sentence, unigrams, where you split on one thing. This tries to address what I just talked about, that long-term dependency, where you can get unigrams. This is a sentence. Bigrams. This is a sentence. And trigrams. This is a sentence, right? This is where we try to model in terms of like a dependency that we can keep track of. You can probably already guess that this also struggles to get long-term dependencies, because you get up above like pentagrams and things tend to get really memory heavy as you're going through this. Beyond that, it also ends up taking words as words. And you can try to fix that with tokenization, but a lot of the time the n-grams that you get out of it, the computer doesn't know what to do with them by themselves. I'll give you an example with nationality, right? Nationality is a word that is made up of several parts. And if we take those parts, if we take that word apart, we can glean information from every individual part. And we can glean more information from it that way, or at least a computer can glean more information from it that way than taking the whole word at once. We found this is the reason for like subword tokenization, sentence piece, if you've heard of those. And n-grams fail to do that in a really good way. And that's the reason why I gave the perplexity algorithm here. The perplexity of an n-gram goes exponentially up based on how many grams you have per sentence, and number two, based on how much you reduce each word. So let's continue going. This is where we hit that idea that I talked about earlier. Colorless green ideas sleep furiously. This is probably the most famous sentence in 20th century linguistics. This is from Noam Chomsky. And what it demonstrates is nonsense. It demonstrates that each one of these words has a correctly defined semantic value. They all make sense to us. And that's kind of the problem, is because they're used in a syntactic context in which the grammar is completely right, but all of the meanings conflict. Ideas can't sleep. No one can sleep furiously. Green ideas don't make sense. And it makes even less sense for the green ideas to be colorless. Like, all of the words are semantically sound. They're just used in a syntax that renders them nonsense. And what this tells us one more time is that syntax is not connected to language in the way that a lot of people like to think. And let's step into Noam Chomsky for a little bit, just so that we can understand him. He's commented on LLMs recently. He is a brilliant man, shaped linguistics in the 20th century. He also added a lot of hype around cognitive studies, whether that was cognitive psychology or anything else. He put syntax at kind of the center of the theory of language, creating generative syntax, creating transformational generative syntax, and positing that basically syntax is a set of rules that allow you to generate anything, any number of infinite syntaxes or sentences in a language. And that we as humans already have language kind of encoded in us, the same way words have meaning encoded in them. We have language encoded in us, and we just have to learn the rules. So it's kind of fun to see that he's needing to now comment on models, the GPT system of models, or the GPT family of models, that they have syntactic, or they only use syntax to generate. And he's now needing to comment on the meaning that's generated from those models. It's fun to watch. It's fun to be a part of the history that's being made here. So we've gone over a little bit of a crash course in linguistically informed NLP. We've gone over a little bit in why it's hard. Here are some more reasons, right? I've said before that you should hire linguists. I stand by that, but why should you not hire exclusively linguists, right? Number one, linguists are not always specialized in both language and computers. So even if somebody understands all of the problems that I just brought up and all the systems that I just brought up, that's not a guarantee that they're going to be able to solve any of the problems that you want to solve with your large language models, or even know how to build them. Linguistics, unfortunately, doesn't have all of the answers. Linguistics right now is it's basically a snapshot of what language looks like right now. If you go to dictionary.com, that's what language looks like right now. And it continually shifts and continually changes. And that makes it difficult for linguists to be able to tell you how a model needs to look in 50 years, right? They might be able to help you figure out how it needs to look right now and how to adapt it to be able to handle things. But ultimately, you are going to need to you're going to need more than just a linguist to solve any of these problems. And then let's hit why it's helpful. You may have already seen this, where or you may have already assumed some of these points as you were watching. Computer scientists often have to end up rediscovering very foundational linguistic concepts if they aren't informed of them right now. Like, this is something going on continually in our field. And I love watching it. It's really fun, but we can't just skip ahead if we already know the concepts. Again, if you have any trouble understanding if you have any trouble trying to figure out what you need to publish or what should you present in a conference, one of the very easy ways to do it is pick a foundational linguistic concept and test out language models using that concept and then present on that. I'll give you some examples of that real quick. These are all of the language modeling papers that were they presented basic or foundational linguistic concepts in the last 5 years. And I filtered this by only papers that were actually presented at conferences. So it's not just all of the papers that came out. These are only the really big ones that were presented at conferences. You should recognize several of these. You should recognize the Laura paper. You should recognize An Image is Worth One Word. You should definitely recognize Large Language Models or Zero-Shot Learners. That's the GPT-3 paper. Let's keep going. So we want to take advantage of the fact that these large language models only end up using semantics and they don't have access to the full range of the semiotic triangle as far as user experience goes. Like, they don't have access to images unless they're multimodal. And a lot of the time they will struggle to do both modalities. You have to train really, really careful for that. You can understand all of the things they don't have access to. So let's talk about how we can actually make them better through, number one, prompt engineering, which is a very simple but hard to do linguistic concept because a lot of people end up just doing guessing and checking. We'll talk more about this. And number two, syntactic or textual embeddings. And number three, we have reinforcement learning with human feedback, low rank adaptation, parameter efficient fine tuning, and we'll hit hyper networks a little bit too. So prompt engineering, how can you do it right now? I'll give you an example of what this is so that we're on the same page, and then we can talk about what is prompt engineering versus what it's not. So here is a prompt that was given to the T5 during mask language modeling. So this movie was Mask, right? And the prompt, or an engineered version of the prompt, is classify movie as positive or negative, or classify this movie as positive or negative. This movie was Mask. The difference between these two is kind of stark for us, and this has been a really huge point in figuring out that language models actually do know syntax, is by giving them more syntax that explains what the question is or what the task is. All of a sudden they learn better and they do better on those tasks. Here's another example, right? On average, Joe throws 35 punches per minute. A fight lasts 5 rounds of 4 minutes. How many punches did he throw? Joe threw 350 punches. That's not right. That's not the correct answer. But if we engineer it a little bit, and this is a simple engineering, it's just you prep end your answer with let's think step by step, and then allow your language model to generate after that. And all of a sudden, you get not only the correct answer, but it's very well explained, right? In 1 minute, Joe throws 35 punches. In 4 minutes, Joe throws 4 times as many punches as in 1 minute. So he throws 4 times 35, which is 140 punches in 4 minutes. And then 5 rounds, 5 times 140 is 700. So just by doing a little bit of prompt engineering, and you can obviously do either of these. The first one is an example of input engineering. The second one is an example of augmented output engineering. But you can engineer any side of the prompt to make it more effective for your language model. Let's hit textual embedding now with tokenizers and encoders. The idea here is to give the model a lookup if you already know that when you see a particular token, you want a particular thing out of that token. So in the example in this photo, right, we already know that we want a clock instead of S. And so as it goes through, it gets tokenized, and then we have an embedding lookup based on tokens. We already know that there is a whole embedding associated with a clock. And that embedding in diffusion models like this is associated with a picture. In textual models, it's associated with a particular concept. But when we are able to pass that embedding to the transformer, as opposed to just letting the transformer come up with its embeddings on its own, we're able to influence the output in a very structured way. You can think of this in contexts like customer service, where your company's reputation really depends on you getting the exact right thing every time. And you don't want to have to deal with the backlash of your chatbot responding badly to a customer. You can use textual embeddings to make sure that whenever you have refund, for example, appear, that a particular answer comes out, right? OpenAI have utilized these in the case of ChatGPT. When people ask questions about things that OpenAI considers unethical for a language model to answer, it will spit out a canned answer instead of spitting out the answer that maybe it would have before. There are obviously ways to get around this, but generally you won't need to, right? That's called prompt injection, is getting around the actual textual embeddings. So here is a practical example of what that looks like with diffusion, where we create a textual embedding of this dog. We take 3 to 5 photos. Obviously more is going to give you better. But then you can clearly see that dog within every bit of art that was generated because it had a particular embedding associated with it. So now let's go into, this is for the MLOps people that are interested more in structure and model architecture and how do we get this to fit really well on my 24 gigabyte GPU. I don't have like 1,000 A100s at my disposal. RLHF makes that difficult because you have to copy the model. And the reason why people are interested in this is for instruct data sets, for creating large language models that have a chat functionality or respond better to longer, more engineered prompts. But within this structure, you need to copy your entire model. And so if your model was 10 gigabytes on disk, you now have 20 gigabytes on disk that are just full. And generally 1 billion parameters equates to like 4 gigabytes on disk in FP32. So first thing that you can do to make RLHF a lot easier to handle is quantize, right? You can quantize down to int4, which equates to, if you're doing that math, you have 4 gigabytes at 4 gigabytes for 1 billion parameters at FP32. That goes down to 2 gigabytes at FP16, 1 gigabyte at int8, and then 1/2 gigabyte at int4. So if you have a 10 billion parameter model and you put it in int4, then it only takes 5 gigabytes on disk. And then as we talk about low rank adaptation, that's one way for us to add adaptable matrices into the actual neural network as it goes, or as it is doing its forward propagation and training, in order to train those specific matrices, as opposed to training the entire model. And then that training and those differences end up getting applied to each neuron within that layer. That way it significantly cuts down on the amount of memory the computer needs in order to train each particular layer. The other part is parameter efficient fine tuning. You can think of this similar to OMFIT from Jeremy Howard. It's not exactly the same, but similarly, back when large language, or like the 2016, 2017 version of large language models was happening, a particular way of freezing and gradually unfreezing the model was devised. Parameter efficient fine tuning kind of takes that to the next level, where it says, you don't need to necessarily train all of the layers of the model at once. You can train parts of the model in sequence. You have to keep the whole model on disk at the same time, but this significantly cuts down your RAM usage and your VRAM usage and the overall amount of training that actually needs to happen in megabytes. So these are 3 ways that you can speed up your training and reduce the footprint that it takes to actually use this state-of-the-art method of reinforcement learning with human feedback. So let's look at what this actually does for us. We've talked a lot about linguistics and about the theory. Let's talk about what actually happens when we apply it. So this is from the GPT-3 paper, and this is GPT performance on the superglue scores. The superglue task is, or glue is just general language understanding evaluation. It's an evaluative set of tasks made to help us understand whether or not a particular language model is really understanding language. Models passed the human baselines of glue too fast, and so they made superglue, which is a harder version of the same test. And so this is the performance out of 100 on superglue. The x-axis is the number of parameters that the model has. You can see the blue line is just prompt design, right? It takes a lot of effort in order to, so this is the same as prompt engineering. It takes a lot of effort and a lot of parameters to get significant improvements out of it. However, it is still really good to note that 10 to the 11th parameters, this is significantly better than just fine tuning the model, this is the first pass at fine tuning, right? And then the green arrow is combining both prompt engineering and model tuning. So you can see prompt design is plateauing. Model tuning, just straight fine tuning the model on the particular tasks one at a time, is stagnating, is plateauing. But doing both of them combined, this green line, which is the coolest part, you're seeing a vast increase at every step, and they've actually converged, and the green line is still going up, whereas the orange line is plateauing, meaning that taking into account everything you already know about machine learning, the stuff that we're talking about with prompt engineering and textual embeddings is complementary to it and can only make it better, and it is compatible. So before we go on, I just want to talk about the superglue human baseline is 89.8. And so we can see that both with model fine tuning and with prompt tuning, as we've talked about, which is kind of doing all of these things, it's doing LoRa, it's doing PEFT, it's doing prompt engineering and textual embeddings all at once, we are already better than the superglue human baselines. And so before we move on, I just want to plug my channel real quick. My username on YouTube is I'm Jones. If you go to this link, this is a video showcasing kind of everything that I'm talking about here, how to do textual embeddings, how to do dream boothing, how to do prompt engineering for things. And I'm going to showcase some of the results that we've gotten. This should be pretty fun. So first off, we have Pokemon. If I type into Stable Diffusion that I just want a fire ghost type Pokemon, this is what I get. And you can see there's same coloration and a lot of jagged lines like Pikachu. It looks like it's on a card. It's not a really good representation, what a fire or ghost type Pokemon is, but you can see where it's at least getting these ideas from of what it should look like. If I do prompt tuning, or I essentially prompt engineer a prompt, tell it masterpiece, tell it best quality, tell it photorealistic, I end up getting something more along these lines. If I really construct the prompt and give it everything that it needs, it ends up looking like this. This is a fire ghost type Pokemon. If I take this a step further and do not like I really engineer my prompt to make it super explicit as to exactly what I want, describing every piece of it, here's what I get for a fire ghost type Pokemon. It looks almost like a Ghastly with this this eye here, right, coming around. Really cool. And this is just with prompt engineering. It's just changing the prompt. It's not even adding anything else in. So let's add more in, right? Let's Dream Booth a Ceruledge, which is a fire ghost type Pokemon from the newest games. And this is when I prompt and ask it for a dragon type evolution of Ceruledge. So I've added Dream Booth, I've added Textual, or I've added a Dream Booth, so it has a model already to work with. This is with just a vanilla prompt. If I do some prompt engineering, this is what I end up getting out of it. Really cool. It looks like it could be concept art. If I then take away the prompt engineering but do textual embedding, so this is plus textual embedding plus Dream Booth minus prompt engineering, I get this. Again, really cool. If I add all three concepts together, though, I do Dream Booth, I do textual embedding, and I do really, I'll say concentrated prompt engineering. This is what we get. And I'm incredibly happy with these results. What would a dragon type evolution of a fire ghost type Pokemon look like? I think it's really cool. And then here's what we get if we do, again, so take everything away. We only have a vanilla prompt of David Attenborough in his natural habitat. Right? I think it's pretty funny that like it's his face on some creature, not sure what it is. If you aren't aware, just for those of you who aren't, David Attenborough worked, I'm not sure if it was for National Geographic or BBC, but he worked out in nature doing nature documentaries for a long time. I can guarantee you've heard his voice before. So this is what David Attenborough looks like with some prompt engineering. Pretty good. So let's take away the prompt engineering and add textual embeddings. This is what he looks like. And now let's add prompt engineering and textual embeddings. And like the prompt engineering here is really cool to me because I actually took his name out of the prompt and ended up just describing everything that I wanted to see about this picture. And this is what we get. So you can see all of these add benefits to what we're trying to get at, and using them in conjunction with each other, you can get really good benefits. I mean, it's kind of obvious if you look at it for long enough that it's still created by AI, but it's getting a lot more realistic, especially on a difficult to generate face. So here is another portion. This is a demonstration of LoRa and PEFT, where you can see a large language model running locally on a Raspberry Pi. And I've SSH'd into this Raspberry Pi from Windows, but it's basically just it's unsped up. It runs pretty slowly. But I ask it, what's something everyone should know about large language models? It says large language models are capable of learning from massive amounts of data, which makes them more accurate than traditional machine learning systems and natural language processing tools that use smaller data sets. Cool, right? So we're getting to the point where we can actually run these models on edge devices, which I really am just so excited for. So here's a language model that I ended up training myself. This is a I love Star Wars, and over here, these are not from the language model. This is just showing my very first Star Wars language model, which is a bag of words model that I generated word clouds from based on masks of characters. Right, so this is my first attempt at a Star Wars language model, and this is my latest attempt at a Star Wars language model. It's a 20 billion parameter multimodal Star Wars language model that you can see here pretty clearly is outputting Luke. It trained on every image from all of the films and TV shows, and it trained on every line from all the scripts up until March. And I've been using it to create new characters and believable environments. I've been using it to replicate. This is trying to replicate KOTOR. This is what I always thought it would be fun if Revan had like a bigger lightsaber than everybody else, but so that was a fun concept to generate with it. And again, generating new characters, new ideas for characters, where a lightsaber is like she has two lightsabers generating or turned on her cowl. So it's creative and it's sticking to the Star Wars universe. It's adding to the lore. It's kind of cool, and it's even able to generate Darth Vader. So it's sticking to the current lore and being able to add to it based on the foundational principles that it's learned from the games and the movies that it trained on. One of the cool things that I'm excited to show you is it is even able to generate video. And here's a little I think it's 1 second, maybe 3 seconds of a clip from Star Wars as an anime. And it obviously trained on this clip, but it didn't use the clip as a reference when I asked it to generate this. That's pretty believable, right? I'm really satisfied with it. And it's only going to get better as we get better at putting larger models on smaller devices. So let's talk about where these ideas are actually going. Right, we have ignored phonetics this entire time, partially because I really strongly believe that phonetics is the next place that we're going to need to model. And I've already worked on this for a long time. Here's my first pass at trying to, I'm going to check my volume really quick. Here's my first pass at trying to model phonetics, where we make someone's mouth in a pre-existing video clip move as if it is attached to a particular audio clip. So here's President Biden.
Your fantasies can't ever be quenched, can they? You freaking bricks! When will you learn? When will you learn that your actions have consequences?
So I don't think that's fooling anyone that is President Biden. And so we can go a step further with these multimodal models, where we can generate not just audio, but we can generate animations for the audio. This was just animations, and we're moving to audio. This is a model that I previously created as well. So I didn't create the base model. The base model is Tortoise, if you want to look that up. But I made the model a little bit better. You know, I trained it on new data. I recreated the voice quality variational auto encoder, and I allow it to generate animations as well as audio for a picture. And this is Russell Brand. If you're unaware of who Russell Brand is, you don't need to know about his career or anything. What you do need to know is his accent is a strong amalgamation of several different English-speaking countries. And so you'll hear from this. I'll let you listen.
Thanks for joining on this voyage towards truth and freedom. In this episode, you can't believe your eyes and ears because I am a deep fake. And the amazing thing is, I can make anyone say anything.
Kind of cool, right? But anyone who's heard Russell Brand before knows that this is not his voice. Mostly because it's American. It's in the correct register. It's getting the pitches correct. But just because his accent is all over the place and it's not adequately represented in the training data, it ends up it takes an average and gets American, which doesn't really help. I've since made a lot of improvements to this, and the picture quality is not as good. The animation quality is not as good, but you'll hear from the voice, it's a lot better. And this is audio that you can actually clean up using something like NVIDIA Broadcast and get an almost identical performance from.
Thanks for joining on this voyage towards truth and freedom. In this episode, you can't believe your eyes and ears because I am a deep fake. And the amazing thing is, I can make anyone say anything.
I would wager that if you cleaned up this audio, it would be difficult for Russell Brand himself to know whether or not it was him talking, which is really, really cool. There are companies popping up all over the place. One of the ones that I know of is Bunked.ai. Cameron Bell is one of the founders. But if this makes you nervous at all about being deep faked or having voice acting or something along those lines disappear as a career, I would look into stuff like that, because that's something that I don't think we need to worry about yet. All in all, I hope this was very entertaining for you guys. This is me. Please feel free to contact me on LinkedIn or subscribe to my YouTube. Look up my stuff on GitHub. You can see, like, I have a foundational notebook for text to video. I have a lot of resources for NLP, and I would love to connect with you. So thank you so much.
Yeah. And please contact me on any of these platforms. I'd like to open it up to you guys right now for questions, if you have any. Oh, good question. So textual embeddings involves putting sample prompts through both your tokenizer and your textual embedder. In diffusion models, that's usually a variational autoencoder, if you're familiar with the VAE. You put a sample prompt through and see what comes out. So you can then create an embedding for a new token that has never existed. Like for the Serral Ledge, I used Pokemon ZWX because I'm never going to type that accidentally, you know. And you train that one token and see what comes out as an embedding, and then you train that embedding going through your model on like 3 images of what you want. 3 is the minimum. I mean, I ended up using 5 because I was a little worried that 3 wouldn't work, but it's cool that it can get that performance on 5, right? And the reason I was saying textual embeddings and Dream Booth kind of in the same sentences, they're really similar algorithms. Textual embeddings are a little bit more lightweight. Dream Booth is where you like wrangle the model and force it to recognize a new embedding. You completely train your tokenizer over again and your embedding model all over again. And you can even add in, for diffusion models, the UNet that's actually doing the generation of the diffusion. Does that make sense? So it's retraining only part of your pipeline. That's why it's significant. Right? Yeah. That's exactly what I'm hoping to highlight with this, is that there are a whole bunch of people that are super specialized in computer vision or NLP or, you know, time series. And they end up getting like a little bit of blinders on and thinking that like none of these other specializations is coming up with things that they can apply. One of the reasons why I think OpenAI and Google and these larger companies have been able to push ahead in this realm is by connecting those people and having them just try it. You know, like, hey, this worked out in our computer vision department. Why don't we give it to the language people and see, like, can you make it work? And generally it has, and that's really cool. Go ahead, Eric. Yeah. Well, I'll tell you, I know that like if I know about LoRa and PEFT, like they're already using it. If you're wondering about how OpenAI was able to decrease the price of GPT-4 to like 1/10 of what ChatGPT was, it's because of that. You know, they're optimizing it. As far as what do I think they will do in the future, I think that the moat of reinforcement learning in language modeling is going to keep getting bigger because people are used to GANs. They're used to that adversarial sort of paradigm for it, but this is tandem working towards a reward with proximal policy optimization, and that is like, it's hard to understand, and it's giving them kind of a tech edge in this area. I think that's going to continue. Go ahead. Yeah. Yeah. I like that. Yeah. So when I started getting into this, I started using set tokenizer vocabs for it because your tokenizer vocabulary comes pre-trained with whatever model you're dealing with. And basically just went from there. I went, what are the scalars? What does the vector look like that comes out of the tokenizer, and realized, it's splitting words in places that I never would have split those words. I didn't learn that that's a prefix when I was in high school, but the model cares about it. So why don't I try just putting that through by itself and see what comes out the other end? And you don't have to do it by hand like what I'm describing. You can do it algorithmically. Pretty cool, right? I really like what you're saying though, because in that programming language theory, decreasing the subset actually adds ambiguity in linguistics, which is kind of fun. Many of you have seen The Office, the why use lot word when few word do trick, right? See world, right? Your subset is really small and you have semantic ambiguity immediately because of the small subset, right? And so the prompt engineering is exactly as you described. It's trying to reverse engineer that ambiguity that was created as we're abstracting these terms. Yeah, you did. That's a good question. Oh yeah, there are tons. So that's a fantastic question. I'm glad you asked. So naive Bayes is something that a lot of people still consider to be a baseline for language modeling because it is so accurate on so many classification tasks and it's fast. It's easy to implement. It's really cool. No, you do not have to use naive Bayes, and there are dozens upon dozens of improvements. Even the n-grams that I was talking about, we didn't get to that, but one of the reasons n-grams is a problem is because your vocabulary ends up exploding. Like if you do quadgrams, it's already gigabytes. But you can keep following the progression of things. Naive Bayes is from 20th century. If we want to go into like 2016, 17, we have the advent of the long short-term memory, the first language models that we're trying to keep track of sequences, sequence models, and then you have BERT, you have GPT models. Even GPT-1 is one of the papers that I had in there. And we get to the bigger ones like ChatGPT now. There's been a really cool progression to watch, and it's really fun to keep track of. I'm glad you asked. Thank you. Go ahead. Merging model weights. Could you explain what you mean by that? Okay, sure. Yeah, the web UI. Cool. That's cool. I haven't even tried it. That's really cool. That sounds like you're trying to get a job in graphic design, right? I can just merge whatever I want into this big old monolith model. That's super cool. I really like it. Any other questions? Go ahead. That is a really good question, and it's going to depend entirely on your model pipeline. So if you are a BERT encoder-based pipeline, I'll use that as an example. A lot of people really like BERT. You're going to want to go algorithmically, again, based on the outputs that you're getting from your model. right? If you find that you just give BERT a vector to classify, and let's say it's just a binary classification, positive, negative, you want to look at what comes out, and you can use, I think there's a BERT explainer. There are a lot of different explainer modules so that you can analyze individual tokens and start to get a good sense for which tokens the model considers to be really important in determining the outcome. And then you can design prompts around either using or not using those tokens. Sometimes it doesn't like coincide, like I said, with our human vocabulary. A good example with BERT is abhor. Abhor is a word that I tend to think is really negative, right? It's like to really hate something. But BERT as a vanilla model ends up determining that as like a really strong indicator of a positive sentence, whereas abhorrent is negative. And like knowing that knowing just that one little piece of dichotomy, you can then start to like create a prompt or modify already existing prompts. Like if you're working with a data set already, you can modify your data set to get what you want and to get a really strong confidence out of it. This is especially effective during training, right? Because you want to be confident in your inference at the end of it. Does that answer your question? Is there more? Cool. Yeah. You're asking questions that nobody's solved yet. Look at you. The way that a lot of people have been getting around this is by giving the model context beforehand. Like if you've interacted with the GPT-4 model at all, it has a whole separate space for you to input context for the model to behave in. Like you are a lead programmer who is helping me figure out the best way to use Python right now. You can give it that context and then it will use that context to help determine what's the best answer. But no, that's unsolved. We would love to be able to insert pragmatic and semantic knowledge, just like inject them into our models, and that's really difficult. All right, if that's everything, thank you guys so much.